Well, thanks for a nice introduction. My name is Anke Reinschluessel, and I'm from University of Bremen. I'm going to present my work on, oh sorry, I have to stand here, right? On guiding biopsy needles with a custom display, and it was done with the help of my co-authors from Howard Medical, Brigham Women's Hospital, Massachusetts General Hospital, University of Kaiserslautern, and of course, University of Bremen. So, what do we see here? I will tell you during my talk what this picture has to do with this piece of paper and an electroluminescent display. But first, what do we see on the picture? This is a very uncomfortable position. It's a very narrow workspace, and it looks kind of unergonomic. What it's done here is a process called MRI-guided biopsy. So what's an MRI-guided biopsy? Biopsies are a process which is done when someone is expected to have cancer. So we need a sample of the tissue that's thought to be cancerous. In my case, the sample is prostate cancer, which is the most common cancer in men. So we take a sample. We need a needle to take this tissue sample. It's a very thin needle. You can barely see it on the image here. So it's like here. It's really, really thin and like this. So we need this, but we don't poke in the dark. We use the MRI to guide us where to go. So what an MRI is, I will go into detail a little bit later. But it has a very good resolution of soft tissue. So when it looks different on the MRI image, it might be cancer. And still we don't poke like somewhere where we want to. For this prostate biopsies, there was a template developed. It's a needle guidance template, and it's like roughly 10 to 12 centimeters big and has 210 holes. So the holes are apart by 5 millimeters, and it's pressed against the skin between your legs. So there's no air in between, it's really tightly pressed there. And the needle, which I just showed on the last slide, is just put through one of the holes. It nicely fits there. You can see one of the templates on the left side is actually the same template. On the right, you can see all the frames which is attached to when it's put in the MRI. So they have some more help in figuring out where to put the needle. They have actually a nice computer program. This computer program takes all the MRI images that are taken from the patient in the MRI. Also, you can see the template. It has some nice markers, so you can calibrate the whole program where the template actually is according to the patient. So you have an overlay of all the 210 holes in this image, so that the computer program knows where the holes are, and then the doctor can look at the image and can see the prostate. No, you can't see my mouse. You can see me. Doesn't this work? Yeah, that's the prostate. Every physician knows that. I had to learn that. So you can say, okay, this looks different, this looks different, this looks different. I want to take samples of this and this area. So it marks it like you had here. You have like these nice stars. Then the computer program can say, okay, you have to go to this hole, and this hole of the template, and then you get exactly the samples you want to have. So that's pretty handy, right? Okay, holes are nicely calculated. The template is somewhere in the MRI. Now we have to get the information on which holes we have to poke through into the MRI. And this is where this nice sheet of paper comes into. Because we have a representation of the template on this paper. You can see it on the right-hand side here. That's on this paper. So they really go on like marking each target on this piece of paper, because the computer calculating all these targets is standing outside of the MRI. So they take this piece of paper, go into the MRI and OR, and then they go like, okay, I have to go into G-1, okay? And then they poke. Yeah, well, and remember that was a really small template, 14 by 15 centimeters and 210 holes. Sounds not so easy. Just to sum up the process, we have the MRI, which is like not real MRI, but to make a sketch. The patient is laying at the isocenter of the MRI, which is like roughly 50 centimeters from the enter of the MRI, where the doctor stood in the beginning of the talk. That's where the best resolution is of MRI images. There also the template is standing, and it will be there during the whole process. It won't move, because then the resolution is bad and then everything is messed up. So nice holes are nicely calculated, and then the paper is taken with them into the MRI room and taped on the MRI. Because the working space, this paper is still not sterile, can't be used like any closer to the patient. And this is where I thought, like, I can help with that. So, but first, what's an MRI? Does anybody know what's an MRI? Like, okay, 2 persons. It's a magnet, 3 persons. It's a very, very strong magnet. They are like from 1 to 5 till 7.0 Tesla. So it's really, really strong magnet. Provides very good images of the soft tissue of the body. So I got a few MRIs of my head so you can really see what the brain looks like. It's pretty awesome. It doesn't work on X-ray. So X-ray is more for the bones. And the one other thing is it's very loud. You get really headache from it. And the big bore MRIs are 70 centimeters. It's like roughly 27.5 inches. So it's not really big. So magnet, remember that, because developing for MRIs is not that easy. You can't bring any ferromagnetic stuff in there. It's forbidden, actually. When you go into get an MRI, you say, like, take off everything that's metal at all. Every earrings, everything, you are not allowed. So also, most hardware is not allowed in there. So you can't use augmented reality glasses, laptops, not allowed in there. Simply, they might not work because of the strong magnetic field. You get like very awesome looking artifacts. Also, they pose a security hazard to the persons working there. There was one person killed because an oxygen tank was attracted to the MRI and someone got hit by it. Also, like other things, like if you have an implant, the things heat up, so you get really heavily burned. So we keep away from everything ferromagnetic in the MRI. So what can we use to bring like the information closer to the doctor where to put the needle? Everything that's used during this procedure is, by the way, MRI safe. It won't heat up, it won't be extracted. Everything is safe, just not to worry you. One solution are EL displays, electroluminescence displays. They work safely in the MRI, and they don't have anything magnetic on them. They come in, they're very, very thin displays. They're like as thin as this piece of paper. They come in every shape, as you can see here. You have butterflies, you have like a Twitter bird, you have a car engine. You can prototype them in every shape you want to. We have seen them over the CHI for the last few years because Oberling and I started presenting them at CHI 2014 in the following years. I've just seen a talk at the Human Senses session where they worked with the sensor of that. So it was really nicely presented. So you can also fabricate them yourself. It's a screen printing method, so you can build them at home. And I didn't like the setting, so I make a different form. So that's the background in the EL displays. My idea now was, we have this nice computer program that calculates which hole we want to go through, and we have the template. So idea is, we just built a display of EL display on the background, which shows exactly where we want to go. Straightforward, we have a crosshair metaphor, and where the crossing is, our needle has to go. Pretty straightforward. So I built my own EL display. You can see like 2 layers of stripe display, currently just the phosphor layer which emits colorful light, and in my case it's green. So on the right hand side you see all the electronics added. It's copper in this case, so that's not ferromagnetic, totally safe in the MRI. So my prototype. You see in the left bottom corner the the template that is used for the real cases that was still in use in the hospital, so couldn't use it. So I've had my own copy printed. It's the same dimensions, same amount of holes. And now I combined it with the display in the background. So currently, and this is how it looks applied. As you see, it's changing the crosshair. The camera was not very light sensitive. I'm sorry, but you get the idea, right? So we had to test that. User study. What else do we do in HCI? We out-tested the original paper version, so we got them 2 times 3 targets on paper, and we got them the same targets on the illuminated version, which were shown as before. So they got each time one target and 3 targets in a row with the Crosshair metaphor. The software directly was linked to the display, so I clicked on a target and the target was illuminated. The template was placed in the MRI bore. What did we measure? We measured task completion time per target set, for sets of targets. We measured the task load using the NASA TLX questionnaire, the usability by the system usability questionnaire, and we got also additional verbal feedback in the end. Our participants, we had 20 participants, where we had 3 physicians with a domain experience. That means there were radiologists with experience performing biopsies, including prostate biopsies, using exactly the template I showed you. The other 17 participants were research with a medical background. I couldn't use the real MRI because they used it for the patients. They're coming in and out of the hospital, so I built my own replica based on the real measurements, so I had the same depths, the same widths and everything. I used the real patient table, so the thing you see, the feet thing sticking out, that's a real patient table the patient get fixed on during the procedure. So, you see on the right the template placed on the back, that's exactly the depths would be like it would be placed in the isocenter of the MRI. Also, the patient table ensures that we have the narrow workspace like the physicians has in the real scenario. Results. They were as hoped and expected. We had a significant decrease in workload, which was measured by the NASA TLX. That's good, because the decrease reduced the workload. That's what I wanted to say, by 47%, so it was less cognitive demanding. System usability, we had an increase in usability by 30%, so the illuminated template increased the usability of the template. It was easier for them and more nicely. And what about the time? It's also interesting, because like procedures take time, and time is money, especially in the hospital. Needle placement time, we had also a significant decrease. If you look at the median, it is about 50% decrease, so they were 50% faster using the illuminated display. Also, if you look at the whiskers of the box plot on the right-hand side, the blue one, we have less variance, so the people were more consistent in task performance, independent of where the targets were. We distributed them very evenly over the template. Because if you have something in the top left corner, it's way easier to target than something in the middle where you have to count very carefully. So, we had a more closer look on the times. So on the left you see overall participants, we mixed here the doctors and the researchers. On the right-hand side you see just the researchers, and this is the doctors. The top one might look as an outlier, but actually that's the middle time of one doctor who had like some questions during the first run, and the second one was 50 seconds, so it was perfectly in the middle, but it averaged over to 90 seconds. But still, the doctors were like as the researchers in the middle, so it's fine that we mixed them. So about the verbal feedback, the participants said like might be nice if the lines were a bit brighter and a bit thinner to increase the visibility and differentiability, but well, it's the first prototype. One participant said like the counting, the manual counting was really, really annoying, so the illuminated version was way better. And 2 participants actually really said like, oh, I really like the illuminated version, when can I get that? To sum up, EL displays have a good solution when you're working in the MRI environment, because with strong magnet you can really use like a very simple solution which is not any technology that can be disturbed by the magnet. We didn't change the current clinical workflow. That's something really important, because like other technologies that exist, like needle guiding robots, the physicians have to learn a whole new workflow, and they don't really like that. We were significantly faster and better in terms of task load and usability. And for the future work, we want to integrate the display completely into the templates, so we have better consistency. And we want to test the display in our IOB-approved study under real conditions on patients. That's where you further work. Well, just to complete everything, that's where the images are from. Also, everybody said, like, we have open PhD positions. We do that too. So if you want to come to Bremen, it's a really nice city, and do their PhD there. There's some information, and thank you for your attention.
We have some time for questions. I have more questions. So I'm really impressed. This was a nice talk. And this is a question coming from someone who doesn't know anything about biopsy needle placement and know nothing about the operation, the procedures. I'm curious, like, do they have to confirm, like, if when they place the needle, like, and then is there any way that the system can feedback them, whether you place it right or not, or like how does the whole workflow look like?
Actually, when they have the hole, and they put in the needle for a bit, and then they run an MRI and check if the needle went in there where it's supposed to be, and then they go step by step further, always confirming again where the needle is, and again and again and again, if they really reach the target and at the depth they want to go, because also the needle is slightly flexible and it sometimes bends into the prostate, and if the prostate is cancerous, it also changes in density, which they can't really account for yet. So they have to try anyways a little bit.
So does the system then, if you found you kind of poke in the wrong place, does it change the dot or something?
The system already calculates when the patient is moving due to breathing between two image sets, so it changes dynamically. Okay, now you have to go through this hole for the next one. That already does. If the needle is in, not yet, it doesn't track the needle. That's something further I want to do.
You were saying that you were going to try to put this into practice. What are the steps that you see to integrate this there?
First, we have to really integrate all the electronics into the plastic acryl block, which is the template, so that's easy sterilizable because we don't want to throw away it every time. At the moment, they sterilize the whole template, and then we have to get the IRB approval. As I said, we need to get a list of approvals from the government of the United States to put that into work.
But you don't need any sort of medical device sort of process to appear? Is it a purely mechanical procedure that you need to ensure that this
the improvements are like from medical and hospitals, that the hospital says, okay, you can put that on a patient.
And it's okay.
If they say it's okay, it should be pretty easy because it's nothing mechanical doing something on the patient, it's just illuminating, so it should be pretty straightforward.